Good morning, everyone. We are from Group 6. This is our group members, which is me, Hui Chun Wei, Avin Dun, Amira Shahira, Muhammad Amin Nasaruddin, and Kinesh Raj. First of all, for our simulation 1, we are varying the channel length of the MOSFET to obtain different graphs and their parameters. For device 1, we have set the channel length to 50 nanometer to obtain the IDVD graph, and the graph of surface charge against gate current, gate voltage. For the IDVG graph, we can obtain the threshold voltage by setting the drain current to 1 times 10 power of negative 6 amperes. And also we can obtain the in-gauge current and on-saturation current by setting the gate voltage to 0 and 1 volt respectively. Then after some calculation, we will get the DIBL value and the sub-threshold swing for saturation region. This process is same goes to device 2 and device 3. For device 2, we have set the channel length to 40 nanometer, whereas for device 3, we have set it to 30 nanometer. So this is the graph and the parameter that we obtain from device 2. And this is also the graph and the parameter that we obtain from device 3.
Here we can see the comparison between device 1, device 2 and device 3 in terms of channel length, threshold voltage, on current and off current, drain induced barrier lowering and sub-threshold swing. So we change the channel length for the N-channel MOSFET where device 1 is 50 nanometer, device 2 is 40 nanometer and device 3 is 30 nanometer. The observation that we could make from the channel length variation is that threshold voltage decreases when channel length decreases. This is called short channel effect. This happens because when the channel length is reduced, the depletion regions around source body and drain body PN junction start to overlap, and the barrier for lateral injection from source to channel will be decreased. Thus, this barrier lowering leads to lower threshold voltage. The second observation that can be made from the channel length modulation is that as channel length decreases, off current and on current increases. Off current is off-state current where it is measured at VGS equal to 0, where I on is current flowing between the source and drain after the MOSFET is turned on. This is because the resistance is proportional to the channel length. When we shorten the channel length, the resistance becomes lower, causing the off current and on current become higher. The third observation that can be made from the simulation is that the drain induced barrier lowering, or known as DIBL, increases when the channel length decreases. DIBL is a short channel effect in MOSFET referring to a reduction of threshold voltage of the device at higher drain voltages. Due to the lower threshold voltages at VD equal to 0.05 and VD equals to 1, when channel length decreases, the DIBL increases. The fourth observation is the sub-threshold swing, which we can see that from 15 nanometer to 40 nanometer, it was decreased, then rise back higher for 30 nanometer. Sub-threshold swing is theoretically should be 60 mV per decade at room temperature for a conventional MOSFET, yet experimental sub-threshold swing for a scale MOSFET at room temperature should be around 70 mV per decade. The value might slightly have degraded due to the short channel MOSFET parasitic. In terms of that, we can see that the value we obtain is 78.75 mV per decade for 50 nanometer, 76.25 mV decade for 40 nanometer, and 78.33 mV per decade for 30 nanometer, where in the range of proposed theoretical explanation, which is in the range of 70 mV per decade.
The fifth observation from the solution is related to the surface charge. Surface charge is the amount of charge that needed to be injected into the gate electrode to turn on the MOSFET. If the surface charge higher, it will take time to charge the capacitor necessary for tuning on the MOSFET. The surface charge decreases as the channel length decreases. The highest surface charge is for 50 nanometer, which is 1.39 power of 13 centimeter square, then 1.35 power of 13 centimeter square for 40 nanometer, and lowest is for 30 nanometer with the value of 1.3 power of 13 centimeter square. This shows that short channel can achieve better switching speed and lower the switching loss due to lower surface charge. From all the observations above, we can see that changing the channel length will influence a lot of electrical parameters. This is due to the short channel effects, which consequences arise while the channel length is that the same order of magnitude because the depletion layer width of the supply and drain junction. In MOSFETs, channel length should be bigger than the sum of the drain and source depletion widths to avoid the edge effects. There are a few ways to improve the short channel effect, and one of it we can do reverse short channel effect. In MOSFET, reverse short channel effect is an inverse of threshold voltage with decreasing channel length. This is opposite with common short channel effect, and the difference comes from changes in doping profiles used in modern small device manufacturing. The process of reverse short channel effect is related to the halo doping, which in order to combat drain-induced barrier lowering (DBIL), MOSFET substrate near source and drain region are heavily doped to reduce the width of the depletion region in the vicinity of source substrate and drain substrate junctions. In the case of short channel lengths, the halo doping from the source overlaps that from the drain, which increases the doping concentration of the substrate in the channel region and thus the threshold voltage. This increased threshold voltage requires a higher gate voltage for channel inversion. The length increases, halo doped region separate, and the central doping channel approaches a lower background level dictated by the body doping. This decrease in the mean channel doping concentration means that VTH initially decreases with increasing channel length, but approaches a constant length value for sufficiently long lengths.
For surface charge graph for the first device, which is aluminium, we can see that to calculate the DIBL, we will use the formula VTH for first VD, which is 0.05, minus VTH for second VD, which is 1 volt, divide by delta VD, and we will get the answer is equal to 0.07895. And for the SS, the calculation is VTH over 3 decibel. So the VTH is 0.235 divide by 3 decibel, and we will get the answer is equal to 78.33 millivolt per decade. So for the second device, which is molybdenum, we can see that the first graph is ID against VG, the second graph is ID against VD, and the third graph is surface charge versus VG. So these three graph is also using same volt VD, which is 0.05 and 1 volt, and the calculation for the IBL is the same, and is equal to 0.39 minus 0.315 divided by delta VD, which is 1 minus 0.05, and the answer we got for the IBL for the second device is equal to 0.07895. And for the SS, like the previous calculation, we need to divide VTH with 3 decibel, and we will get the answer is 101.67 millivolt per decade. And this is for the last device, which is tungsten, and the graph is the same. We have 3 graphs: ID against VG, ID against VD, and surface charge versus VG. So the DIBL calculation is also the same, just different value, because our VTH is different, right? So 0.85 minus 0.775, and we'll divide with 1 minus 0.05, and the answer we get is 0.07895. And lastly, for the SS, for the last device, we need to divide the VTH, which is 0.31, divided by 4 decibel, and equal to 77.50 millivolt per decade.
Comparison between different gate electrode materials. So we have tested for the 3 kind of gate electrode materials, which are tungsten, aluminium, and molybdenum. So the work functions of tungsten and aluminium has not been specified, since it has been already in the list in the simulator. But then for the molybdenum, we put the work function of 4.6 to simulate it. Here we can see the value of VTH, I off, and I on that we obtained from the IDVD and IDVG graph. Apart from that, we obtained the DIBL, same for all of the materials. Other than that, the sub-threshold swing for tungsten is 77.50, for aluminum is 78.33, and for molybdenum is 77.50. So the explanation will be given further. The first observation from the assignment: when we change the gate electrode, the threshold voltage changes. We can see that tungsten has the highest threshold voltage, followed by molybdenum, and the least is aluminum. This is due to the work function difference of the various gate electrode materials. From the threshold voltage formula, we can conclude that the higher the work function, the higher the threshold voltage. Hence, the simulation results prove the theory. The molybdenum has quite strange results because the nanotube simulator does not have molybdenum material, so that we have to enter the work function manually, which is 4.6. The second observation that can be made from the simulation 2 is that the higher the work function, the lower the on current and off current. This is due to the increase in threshold voltage when work function increase. In addition, the ID formula could show how the changes in VTH could influence the on and off current. So we can see the table, the cutoff, linear and saturation region, and we can see there how the VTH influence the ID.
The third observation that can be made from the simulation is that the drain-induced barrier lowering DIBL never changes regardless the work function difference. This is because the channel length and oxide thickness kept the same in the simulation. DIBL is a short channel effect and it would not change if we just change the work function. The subthreshold swing slightly change where it increases a little bit when the work function decreases. Subthreshold swing is theoretically should be 60 mV per decade at room temperature for a conventional MOSFET. Yet, experimental subthreshold swing for a scale MOSFET at room temperature should be around 70 mV per decade. However, the subthreshold swing is still in the range of 70 mV per decade for our simulation and it is acceptable.
Next, from all observations above, we can see that different gate electrode materials will give different work functions. Therefore, will influence the VTH, I-off, I-on, DIBL, and also subthreshold swing value by following the type of gate electrodes. The gate electrode and the source or drain formed by ion implantation represent the regions where voltage are applied to a MOSFET. The gate electrode also may be composed of polysilicon, a silicate material, or metal composites. The specific material used depends upon desired work function of the gate and device type, also the required device electrical parameters. Besides, a study found that the work function can be controlled by the thickness of the underlay metal, which is the layer closest to the outside. Depending on the amount of diffusion, the influence of the overlayer on the atomic concentration at the dielectric interface varies. Next, the purpose of gate electrode in CMOS is to shift the surface Fermi level of the channel to the other band edge, either closest to the conduction band or valence band. An MOSFET consists of a p-doped silicon channel. A gate of low work function, which is 4.05 electron volt, will move its surface Fermi level to its conduction band, inverting the channel. Same goes with PMOS device has an n-doped silicon channel, and a gate with work function 5.15 electron volt will shift its Fermi level to its valence band, inverting the channel. This requires a work function change of 1.1 electron volt, the silicon band gap. Apart from that, in order to optimize transistor performance, metals with appropriate work functions for both NMOS and PMOS must be identified and integrated into the conventional CMOS process flow. With that, we end our presentation. Thank you.